in the last couple of sections, we looked at some tests that we can use to figure out convergence or divergence. But the tests that we learned were really kind of specific. We had to meet a lot of criteria before we could even use the test. In this section, we're going to start looking at some tests that are a little more generally applicable. Okay, and the first of these is the direct comparison test. And it looks like this. If I have two series A sub n and B sub n, if this is true for all n, then B is always greater than A, then I know that if B sub n converges, so does A sub n. And if you look at just a little sketch graph, if this is B and it converges, we'll call this one B, and this is A that is always less than B, if this is going to converge, this is going to have to converge. Okay, and there's another part of this that says if A sub n diverges, then so does B sub n. And just, looking at the graph again, if this is B and this is A, if I know that A diverges and B is always bigger, it's going to have to diverge as well. Okay, so this is called the direct comparison test. Let's look at some examples. Okay, so I have a series . One over 2 plus 3 to the n power. And I'm going to compare this to a little bit simpler series. I'm just going to omit the 2 and have 1 over 3 to the n. Okay, and this is a geometric series. And we saw earlier that it was convergent. Okay, so term by term comparison. If this is A sub n, we could write this one as 1 over 2 plus 3 to the n. And over here I'm going to write 1 over 3 to the n. And call this V sub n. I'm going to talk about n greater than or equal to 1. Now looking at these two fractions, this one is always going to have a larger denominator than this one. And a larger denominator means smaller fraction. So A sub n will always be less than V sub n. And we already know that V sub n is convergent. So if this is convergent, this must also be convergent. Let's look at another example of using the direct comparison test. Okay, in this example, I have this series. And we'll call this one A. And I'm going to compare it to something that's a little simpler. Again, I'm going to take out the 2. Okay. And from the last section, we know that this is a p-series. And the exponent, p is less than 1, so this is divergent. Okay, so looking at the two terms, if I have 2 plus the square root of n, and over here I have 1 over just the square root of n. Again, this is going to be larger. This denominator is going to be larger than this one, which means this is going to be smaller than this. And this will be smaller than this. But this is divergent, so what do I know about this? I don't know anything. Okay? In order to use the test, I would have to have a series over here that was smaller than this one, and also divergent. Okay, so this is not helpful. Let's try something else. How about if instead of 1 over the square root of n, I just do 1 over n. I'm going to say n has to be greater than or equal to 1. And now when I compare term by term, this being the b part, what's going to be true? If I let n equal, let's say 4, to make our math easy, then I have 1 over 4, and over here also 1 over 4. So at that point, they're equal. After that, let's say I let n equal 5. This is now going to be 1 over 4.4 something, and this will be 1 over 5. Larger denominator, smaller series. So this is now smaller when n is greater than 4. Okay, so now we can say, because we know that this is divergent, that this must also be divergent. In addition to the direct comparison test, there's another test we can use called the limit comparison test. Let's see how that works. Okay, this test tells me that if I have a sub n that's positive and b sub n that's also positive, and the limit as n goes to infinity of a sub n over b sub n is equal to some number L, where L is finite and positive, Okay, if this is true that the ratio of the two series does have a limit and the limit is finite and positive, then both series either converge or both series diverge. Okay, so if I can get this condition, I know that these two series are going to behave in the same way. Let's work an example. We've got a series and you might remember that this is called the general harmonic series. And we want to show that it diverges. And so we're going to compare with this limit Okay, and this is just the harmonic series. This is the general harmonic series. This is the harmonic series. And we already know that this diverges. Okay, so now I'm going to take the limit as n goes to infinity. And 1 over an plus b in the numerator, and in the denominator 1 over n. Now when I clear away those fractions, I get n over an plus b. And when I take the limit as n goes to infinity, I end up with 1 over a. Okay, so I have a limit. The limit is greater than 0. And so I can conclude that these two series do the same thing. Since I know this one diverges, I know that this one also diverges. So I have shown that. Let's look at another example of the limit comparison test. In this example, the sum from n equals 1 to infinity of the square root of n over n squared plus 1. And I'm going to compare this to square root of n over just n squared, which I can rewrite as 1 over n to the 3/2 power. And now let's take a limit, and we'll use this function, or this series first. And then we would divide by this one, but since this is already a 1 over fraction, I'm just going to invert it and multiply. Okay, so now I have square root of n, which is n to the 1/2 times n to the 3/2. So I'm going to get the limit as n goes to infinity of n squared on top over n squared plus 1 on the bottom. Okay, and as n goes to infinity, the 1 really doesn't matter anymore. And so I have infinity squared over infinity squared. So the limit is 1. And since we know that this series was convergent, and we did get a limit that's greater than 0, this series must also be convergent. We're going to look at one more example of using the limit comparison test. Okay, this is the series we want to find divergent or convergent. N times 2 to the n power over 4 times n cubed plus 1. Okay, so a reasonable comparison might be 2 to the n over n squared. So what we did, we divided out an n here, and we took the 4 out and divided out an n here, and dropped the 1. Okay, this series diverges by the nth term test. So the limit as n goes to infinity of a sub n over b sub n is going to be n times 2 to the n over 4n cubed plus 1. And again, I'm just going to invert this and multiply. I have n squared over 2 to the n. Okay, this 2 to the n and this 2 to the n cancel out. So now my limit looks like n times n squared would be n cubed over 4n cubed plus 1. And the limit as n goes to infinity would be 1/4. And again, this limit is finite, and it's also positive. So since this is divergent, we know that this is also divergent.